सर वो एक्सेल માંથી એવું કરना
હા એ જ કરવું
એટલે સીધો ઉતારી નાખો
પતી જાય એટલે ઓલું ભેગું એક મને શૈલેન્દ્રસિંહ નું બાપુનું આવ્યું છે એટલે એ હા બાપુનું એક આવ્યું છે એપેન કર એમ તો એમાંથી જ લીધું છે પણ એમાં છે ને તમને એક ફાયદો થશે સાહેબે ક્વોન્ટિટી એડ કરી છે ડીટી ના ફોર્મેટમાં ક્વોન્ટિટી નથી એટલે તમારે છે ને પેલું આઇટમ વાઇઝ તમારે મેન્શન તો કરવું પડે ને
કરીને આપણે
ફોર્મેટ ડીટી માં ક્વોન્ટિટીમાં એડ કરવી પડશે ઉમેર દો ને ક્વોન્ટિટી ભૂલી ગયા લાગે છે
એવું કરો
હે ને હા એટલે મને લાગે જે હમણાં એસબી પરમાર સાહેબે મોકલ્યું ને એ ફોર્મેટ મને ઓકે લાગે છે એમાં જ બધાનું એડ કરી દેવાય
હા તો એ તો
હે ને?
કરना
ઓકે.
અને ઓલું કોમન હશે ને એને છૂટા છૂટા કરી નાખીશું
હા હા હા
એ પર નાખીશું આ બને તો મહેનત ફટાફટ
હા પતી જશે So dear students, yesterday we discussed a few instructions, assembly language instructions. Is there any problem? You understand all those instructions or any problem? Was it fine? So today we will solve few more exercise. Again, you have to take notebook and pen and solve the exercises. So what will be the content of or status of zero flag and carry flag after execution of following instructions? So try to find out. You have two instructions given on the screen. Am I audible and screen is visible to all of you?
Yes, sir.
Okay, so try to add this ball. So there is a content of R6 is available with you and the content of R7 is available with you. So you have to add R7 and R6 and then you have to find out what will be the content of the status of flag 0 and flag carry. So these are the two register value you have to add. Zero, zero, zero. All if I write in a binary, all this 0 and then 1, 0, 0, 1 and then 1, 1, 0, 0. That is C. This is a C, right? And this is a 9. And others are 0. Similarly, in FF, all these are 1. Right, and 6 means 0, 1, 1, 0. And 4 means 0, 1, 0, 0. So you have to add these things. Okay? So 0, 0, 0, this will be 0, 1 plus 1, 0. Carry is 1, so 1 plus 1 again 0. Carry is 1, so 1 plus 1 again 0. Carry is 1, so 1 plus 1 again 0. Carry is 1, so 1 plus 1 again 0. Carry is 1, so result is also 1 and carry is 1. See? And all these are FF, so that the process will continue. Right? So sorry, this is 1, 0, so it is 0. This is also 0. Then again this carry will continue up till like this. So it will be 0 and at last also carry will be there. So like this, you have to perform the addition and you have to know the status of zero flag and carry flag. So as you can see here, the result is 0. So zero flag is set. And carry is there, so carry flag is also set. Okay. So like this, you have to perform the addition and then find out the status of carry flag and zero flag. Is it okay? Is there any doubt in this? Dhruv, yesterday I have given the responsibility to Dhruv. Dhruv is present.
Yes, sir.
Why you are not giving feedback?
Sorry, sir.
The responsibility is given to you. તારે જ જવાબ આપવાનો એટલે મને ખબર પડે અવાજ મારો સંભળાય છે, સ્લાઇડ દેખાય છે.
Okay.
What will be the content of register R5 after execution of following instructions? So try to find out the content of R5. Perform AND operation between the given data. Who will give answer? 1093 number. Can you give me answer? Dharmi. Dharmi present or not? Dharmi is not present. Physically, she is not, I think, available there. Just started the meeting and then away from the meeting. Amit Pandey. No, Amit Pandey is also not there. Then Talsania Jinay is also not there.
હેલો સર ધાર્મી બોલું.
ધાર્મી શું આવશે આન્સર આનું?
ખબર નહીં એ મને નથી ખબર પણ નેટવર્ક નો પ્રોબ્લેમ હતો. મારું નામ સંભળાડું પણ માઇક ચાલુ નતો થતો.
અચ્છા ઓકે એટલે એવું થયું. ઓલરાઈટ તો એન્ડ ઓપરેશન તો તમે શીખ્યા છો ને. એન્ડ ઓપરેશનમાં શું હોય કે બંને બે ઇનપુટ 0 0 હોય તો આઉટપુટ 0 આવે, 0 1 હોય તો આઉટપુટ 0 આવે, 1 0 હોય તો પણ આઉટપુટ 0 આવે. બંને ઇનપુટ 1 હોય તો જ આઉટપુટ 1 આવે. તો તમારી પાસે આ ડેટા છે, આ બંનેનું એન્ડિંગ ઓપરેશન કરવાનું છે. એન્ડિંગ ઓપરેશન કરીને રિઝલ્ટ શું આવશે ને એ તમારે મને કહેવાનું છે. આવશે ને? આ 1 હોય તો 1 ને કેવી રીતે લખાય બાઇનરીમાં? 0 0 0 1. બીજા 1 ને કેવી રીતે લખાય? 0 0 0 1. પછી 2 ને કેવી રીતે લખાય? 0 0 1 0. બીજા 2 ને કેવી રીતે લખાય? 0 0 1 0. 3 ને કેવી રીતે લખાય? 0 0 1 1. બીજા 3 ને કેવી રીતે લખાય 0 0 1 1. 4 ને કેવી રીતે લખાય 0 1 0 0. બીજા 4 ને કેવી રીતે લખાય 0 1 0 0. તો બાઇનરી કોમ્બિનેશન આવી ગયું. આ એક ઇનપુટ. પછી બીજું ઇનપુટ શું છે તો કે 0 0 ff 0 0 ff. તે લખી નાખીએ. પેલું 0 0 પછી ff એટલે બધા 1 છે ને. સહેલું છે એકદમ, કેમ અઘરું નથી, કંઈ કોઈ જવાબ નથી દેતા. આટલું તમારે નોટબુકમાં કરવાનું છે કે પછી ઓનલાઈન ચાલુ થયું એટલે નોટબુક એક બાજુ પણ આમ મૂકી દીધી, હાથમાં છે જ નહીં, પેન નોટબુક બધું ખોવાઈ ગયું છે. આનું એન્ડિંગ ઓપરેશન કરવાનું છે. આમાં ક્યાં અઘરું છે? આ બંનેનું એન્ડિંગ કરશો તો શું આવશે આન્સર?
0 0 2 2 0 0 4 4.
ઓકે, વેરી ગુડ. આ બધા
સર
જવાબ
ઓલરેડી મેસેજમાં લખીને આન્સર મોકલી જ દીધો હતો.
હા, પણ મને એ મેસેજ ના દેખાય. તમારે અનમ્યુટ
ઓકે
અનમ્યુટ
સર.
કરીને કહેવાનું, કારણ કે મારું આ સ્ક્રીન ચાલુ હોય એટલે કે મારે મેસેજ વાંચવાનું ન મેળ પડે. એટલે તમારે અહીંયા આગળ જવાબ આપવો પડે. એટલા માટે જ કીધું છે ક્વેશ્ચનનો આન્સર તમારે અનમ્યુટ કરીને જ આપવો પડશે. કારણ કે મારું અહીંયા MS ટીમનો એક પ્રોબ્લેમ છે કે સ્ક્રીન શેર કરી નાખો પછી તમે મેસેજ કરવા માટે થઈ અને તમારે બધું બંધ કરવું પડે.
ઓકે સર.
રાઈટ, એટલા માટે. So I think you have given the answer. That's great. So your answer would be, as you told, that it should be 0x 0022 0044. That's correct answer. What will be assembly language instructions corresponding to the following C program? So one C program is given, which is having a pointer actually. So there is a character pointer P, which is pointing to some variable. So that variable, which is actually a character pointer, and this is a variable 0x40000000. So this is a memory location at which this pointer is pointing, right? And value of this pointer, so at this memory location, the value is 0x41. So if you want to implement this in assembly language, how you will do it? So essentially, what this program is doing, it is trying to store this value 41 at this memory location. So this is a memory location 0x40000000. This is a memory location. At this location, we want to store data 41. So we already discussed the assembly language for that purpose. So try to write assembly language program for that. If you have written, I will show you the answer. What you have to do, you have to set the memory pointer. So this is the instruction which will set the memory pointer, right? So we are setting this R2 as a memory pointer, right? So R2 is a memory pointer, which is pointing to the memory location. Then we are transferring some data, that is 41 to R0 register. And then we give the instruction strb, store byte, which is there in R0, where you want to store at the location defined by R2. This R2 will specify the memory location because the square bracket is there. So this square bracket means it is a memory location. So at this memory location, R0 will be stored. So this is actually a pointer implementation in assembly language programming. Because in C language, pointer means nothing but it will point the memory location where the variables are being stored. Is it clear? Any doubt?
No, sir, no doubt.
Write assembly language instructions using condition code for this. If R1 is equal to R3 and if R5 is equal to R6, then only we want to perform addition. R7 equal to R7 plus 10. So we want to implement this. We want to do the addition of R7 and 10 only if this condition will be met. R1 is equal to R3 and R5 is equal to R6. So try to write assembly language code for this. But in assembly language, don't use branch instructions, use condition codes. What is the advantage of using condition code? Who will tell? Khyati is there. Khyati Vegra, can you tell me what is the advantage of using condition code? Khyati is not there. Kausal Bodar, are you online? Look, you having a microphone problem or started the meeting and away from it? Khont Mitali, 55 number. In an online class, this is a virtual presence.
Yes, sir.
So can you tell me what is the advantage of condition code? So when you use the condition code, you don't require to use frequent branch operations. And because of that, you don't require to flush pipeline again and again. Because in our ARM architecture, we are using pipeline concept. And if you will take a branch, you require to flush pipeline again and again. And because of that, the throughput will reduce. So try to write condition code for this requirement. So let's, I hope that you have written it. I will show you the answer. So what it will do, it will compare R1 and R3. If this is equal, then it will compare R5 and R6. That's why EQ condition code is added with this. EQ means if this R1 is equal to R3, then only this is required. Otherwise, if first condition fails, then we don't require to compare other conditions, right? So this comparison will take place if R1 is equal to R3. Then it checks whether R5 is equal to R6 or not. If that is the situation, then it will add. Then add also we have added the condition EQ. So only 3 instructions are required. And think about if you do not have a condition code, then you have to use the branch operations and you require many more instructions to implement the same code. So I think it is clear to all or not?
Yes, sir, clear. Yes.
Write assembly language instructions to initialize value of R1 by 0 and then increment it until it becomes 20. So you have to initialize R1 initially by 0 and then you have to increment value of R1 until it becomes 20. You have to check whether it has reached up to 20 or not. So try to write code for that. So initialization is very easy, that you have to simply shift 0 to R1. And then to increment it, just we are adding 1 to that R1. So we are using add. Then we compare R1 with 20, whether it is equal to 20 or not. If it is not 20, then we take a look. And whenever it becomes 20, we will come out from the loop. So R1 will be incremented by 20. A very simple program using the branch operations. Then there are certain pseudo instructions are there in ARM. So ARM supports few pseudo instructions which is used by the programmers. And assembler basically convert that into the ARM instructions. So for example, ADR, in one of the program we use the ADR to load the address of memory location to the register. Like this, we have written like this, ADR, then R0, and message, MSG. So this message location will be transferred to R0 register. So that is actually pseudo instruction. So we can write it in this way, ADR R0 and then table. Then few more instructions like LDR R3 comma into square bracket R0. That means R0 we are using as a memory pointer, which is pointing to the table. Right? So this ADR is basically known as a pseudo instructions for a R. We can also write this instruction in this way. LDR R0. If you know the address of table, you can write it in this way also. In previous example, we use this instruction. Okay, so equal to sign. So this will allocate the address to memory pointer R0. So that is also valid. So essentially, these pseudo instructions will be internally converted to this instruction. This table will define the data actually. All the data will be specified here after DCD. So this table will be your address, and then at that address the data will be there. So this is even more lookup table program. Earlier we have seen one lookup table program, right? So this is one more lookup table program. I will explain. In this we are using the pseudo instruction. So in pseudo instruction, what is done here? ADR R0 comma list 1. So list 1 is the address where some data is stored here. You can see some data is there, right? 0x11223344 44332211, and some data is there. If you are specifying bytes here, then you have to write DCB. Like if you have bytes like this 0x11, 0x22, 0x33, and so on, then DCB, define constant byte. Here define constant double word. So that's why you can specify a 32-bit word. Then LDR R2 into square bracket R0. So R0 is a memory pointer from where the data will be transferred to R2. And then R0 will be incremented by 4. Automatically, we will switch over to the next data because we are incrementing it by 4. So this data will occupy 4 memory locations. So you have to increment it by 4. Then you are comparing whether you have reached up to the end of the data, because at the end we have written 0 here. At the end of the data. If you are not at the end, then again continue the process, otherwise exit the process. Then these are a few more instructions which is not useful for current program. Just to explain that BFC yesterday we have seen. So for that purpose it is written. For this program it is not that much useful. So some process, because we are getting data from the lookup table to R2 and then we want to process that data. So this we call it as a processing instructions for that. So any processing instructions you can write here. If you want to send this data to output port, you can write that the instructions related to port here. So ultimately, this is only a part which will read the data from lookup table and will store into the register R2 one by one. At the end of program, software interrupt is there. Software interrupt 0x11. Usually, whenever you want to end the program, your program will return to the operating system. So this is actually our user application program. And then after once it is over, you will return to the operating system. So that's why for this instruction is there, SWI 0x11. One more example. We want to copy string to the memory location. So we have a string like this, GEC department, GEC Rajkot, and we want to copy this string into the memory location. How we can do that? And now you can see here we have written DCB instead of DCD. We are writing D because every character is a 1 byte. E is a 1 byte, C is 1 byte. Even the space is also 1 byte. So that's why we have written here DCB. In the label given here is SRCSTR. So SRCSTR is transferred to memory pointer R0. So R0 will be acting as a memory pointer here. Right? And there is another memory pointer R1, which is at the location 0x20000000. So it will point to this particular location where we want to transfer this string. Actually, we want to transfer this string at this memory location. So this is actually a destination memory pointer. So what we will do, we will load 1 byte from here to register R2. So LDRB R2, comma, into square bracket R0. So R0 is pointing to this E initially. So this capital E corresponding ASCII code will transfer to R. And then R0 memory pointer will be incremented by 1 because here 1 is written. In previous example, 4 was written because in that case our data was 32-bit. That means 4 byte. So it will occupy 4 memory locations. So that's why we were writing 4 there. Here we are writing only 1 because our data is byte. So every time we want to increment memory pointer by 1. So next time it will point to the C. Now, after getting data into the R2, we want to store the R2 at the memory location specified by R1. And then after that pointer is also incremented by 1. That means now this memory location will become 0x2000001. And at that location, C will be stored. At this location, E will be stored. Once the operation is over, we will compare R2 with 0 whether we have reached up to the end of the string or not. If we have not reached up to the end, then we will repeat the loop again. So when we repeat it, what will happen? Next time, it will be incremented by 1 more location, that is 2, where space will be stored. Then after D will be stored, E will be stored, and like this, the program will continue to the end. So this program will basically copy a string to the specified memory location. In this case, the specified memory location is this. You can change all, this location always as per the requirement. Then let's do the GPIO programming. The GPIO programming of ARM is somewhat complex than that of the AVR. In AVR, it was very easy, you know. When you write the instructions like this, SBI, and then port D, comma 5. So this will set the PD5 pin of your ARM process, AVR processor. So it was very easy, but in ARM that it's not that much simple. So here, because ARM is designed to minimize the power consumption, and 1 pin has many functions. So you have to switch on corresponding oscillator if you want to use that particular pin. So there is a pin select option is there. Pin select 0, where you have to write the bit patterns. What are the pins you want to utilize in your ARM processor? So whatever the bit positions are 1, those pins you will be using, right? Then there is a direction you have to specify. After selecting the pin, you have to specify whether you want to use that pin as an input pin or output pin. So for that purpose, you have to specify the direction. Then every this register is having a memory address. So that address you have to transfer to R0, right? So with help of LDR instruction, you will transfer this register address to the R0. And then after, from that location, you will transfer to the R1. So it will give us the present position. And then after corresponding bits, if you want to set or reset, you have to use instruction BIC. So what it will do, 0x0303 means all initial bits are 0. At last, it will be 011. So these 2 bit positions will be cleared because we have discussed the BIC earlier. What it will do, it will clear bit position. કઈ 2 bit position ને clear કરશે? પહેલી 2 bit ને, કારણ કે ત્યાં 1 છે એટલા માટે 2 bit clear કરશે. Then further, this R1 will be stored back to that location. You can see. So you have to first copy the content from that memory location to the register, set the registers, and then again you have to store it back. So the process is somewhat complex than the AVR processor. Okay. Similarly, this FI0DIR, so direction pin, you are transferring it to the R0. R0 content will be transferred to R1. ORing operation will take place. So ORing operation will set that particular the first least significant bit, and BIC will clear the second bit because here 0x02 is written. 02 means 0010. So this bit position will be cleared. The first bit position will be 1, and then you are transferring it back to that memory location. So this is actually a GPIO programming for ARM processor. Maybe in the next lecture, I will show you the Texas TIVA board, and we will blink the LEDs in the Texas TIVA board with help of this GPIO programming. But for that purpose, to understand that, all these instructions must be very much clear to you. So that's why I was giving more time while explaining all these instructions with examples. So once these instructions are very much clear to you, then only you will be able to write the assembly language program for GPIO programming. Otherwise, it will be very difficult for you. So we will discuss more about the GPIO programming in a subsequent session, because it is there in other topic. There is an entire topic is for GPIO programming. So we will discuss in depth actually. Now let us look at software interrupt. Software interrupt is basically SWI, and it can force CPU into the supervisor mode. So a syntax is something like this: SWI and then some number you have to specify. And n is a function, is a 24-bit function. So maximum 2:24 calls are possible. You can see so many calls are there. Software interrupt code calls you can use. So this bit number 28 to 31 are for condition code, 24 to 27 are opcode, and 0 to 23, that means these 24 bits are available for us to specify this software interrupt number. So many software interrupts you can give with help of SWI instruction. And it's very much suitable for running privileged code and making operating system calls. These are the few examples of software interrupt. So software interrupt, basically you have to specify function number here. And SWR handler will read the opcode to extract the SWR function number. And once you execute this SWI, that is software interrupt, your CPSR will be saved into the supervisory mode, SPSR, and execution branches to this SWI vector location. So every SWR, and after that, followed by that, if you specify some number, every number has a vector location. At that location, your program will jump and will execute those instructions. And then after it will come back from that interrupt to the main program. So software interrupt handler returns by executing the following instruction irrespective of the processor operating mode. So every time, whenever you want to return from software interrupt to your main program, this will be executed. R14 underscore supervisor mode to the PC, so that your program will return to the main program again. So both above actions will restore PC, program counter, and CPSR, and returns to instructions following SWI in a main program. So in a main program, you are basically writing in between SWR, so it will go to that routine, and then again it will come back to the main program after execution is over. Then few assembler directives are there, area directive, entry directive. In assembly language code, you must have seen whenever we were executing the program in kill IDE, we were using this area directive, entry directive. Entry will basically give us the start of the program, from where your program will start. EQU is useful to assign a constant label, actually, some data to the label. And it's very much similar to define in C language. In C language, we say that define by 3.14159 and so on. So that is very much similar to that. DCB is one more directive which we have used in lookup table, that is define constant byte. This DCW means define constant half word. DCD means define constant word. So these are the directives we are using for a lookup table. So in a lookup table, if your data is in bytes, you have to use DCB. If your data is 16-bit, you have to use DCW. And if your data is a 32-bit, you have to use DCD. Then align. Align is also very useful directive, which will align the address of next instruction. And is also very useful directive. If you do not write and at the end of source file, your compiler will complain, your assembler will complain that there is the end directive is missing. So you will get error like that. So and is also very useful. So these are the assembler directives useful in an ARM processor. Dhruv, am I audible? My slides are visible, or is there any issue?
No, sir, it's visible.
Fine. Then let's look at thumb instruction set. So as I told in earlier lectures, that thumb is basically compressed form of ARM. And instructions are stored as a 16-bit. And in a thumb mode, actually, it is decompressed into ARM instructions and then it is executed. Of course, naturally, the performance will be lower because it is a 16-bit. In a normal mode, it is 32-bit, so performance is great. Right? But it should be used whenever there is a memory constraint is there, where memory is less and you do not have a 32-bit data operation requirement. You are happy with a 16-bit, then only you should use the thumb instruction mode. It provides us a higher code density. So thumb, whenever you use it, it will save the 30% of your memory space. And that's why for a memory constraint systems, this is very, very useful. So optimal is this interworking, combining two sets. So if your compiler can support, you can switch in between thumb mode and normal mode. That is optimal way of working. So this is a comparison of ARM code and thumb code. This the one code is written here in ARM code, normal mode, and this is a thumb mode. The operation remains same, right? Operation is same, but in ARM code it occupies 20 bytes. In thumb code it occupies 12 bytes. So you can see here the memory saving. 8 byte is saved here only for this small code. Because here every instruction will be 16-bit in thumb mode. In this case, this is a 16-bit instruction. But the same instruction here is a 32-bit instruction. Okay, because we are using thumb mode. Your intention here to transfer 0 to R3, and 0 doesn't require a 32-bit. So we can use thumb mode. So here this 0 is 16-bit. We are transferring this to R3. So this instruction 16-bit. This is 16-bit. This is also 16-bit. So in this case also, all these instructions are 32-bit long. So overall, if you will calculate here, this is a 2 byte, 2 byte, 2 byte, 2 byte, 2 byte. So there are 5 instructions, right? And here, if you calculate here, sorry, 4 bytes are there for every 8-bit means 1 byte, so 4 bytes everywhere. So 5 into 4, so 20 bytes are there, right? Here, number of instructions are 6. One more instructions you require to accomplish the same job. But every instruction is a 2 bytes. So 6 into 12, 12 bytes are. So this is just a comparison why this thumb code will provide you a better code density. It requires less memory space. So it is good for a memory constrained systems. Then thumb instruction set is more traditional because we cannot add condition code along with the thumb, right? And two address data processing instructions. That means we cannot in a thumb, we cannot write like this, add R1, R2, R3, LSL to this. We cannot write because this will require a 32-bit, right? So we cannot write in this way in thumb. In thumb, we can say simply R1, R2. So R1 and R2 will be added and the result will be saved back into the R1. That we can do in a thumb because it is a 16-bit. So we cannot specify many things there. We can also not specify condition code along with that. And access to R0 to R0 to R8 is restricted to all these instructions: move, add, and CMP. Push pop for stack manipulation is available. Descending state is implemented, and SP is hardwired to R13. As all of you are knowing that R13 alternate function is a stack pointer. Then there are no MSR and MRS is available. That means you cannot transfer status register to the status, that is CPSR, to the registers, and then again from register to CPSR. So these instructions are not available in Thumb mode. And must change to ARM to modify CPSR. That means you can change using BX or BLX. Branch with exchange or branch and link with exchange that you can use. So ARM entered automatically after reset or entering in exception mode. Maximum 255 SWI code is there in a thumb mode. In normal mode, there are 2:24 SWI calls are there. But in a thumb mode, only 255 SWI calls are there. Okay, so let me discuss this last slide. How to add the elements of array. So we have some array. Many locations are there, and we want to actually add, and all that locations are there in this memory locations 0x400000. The number of elements are there in R3. So what we do, we load the data from memory location to R1, and then it is added into the R2. And then we increment R3 to know whether the number of bytes are over or not by subtraction process, and then we compare it with 0, whether we have reached up to 0 or not. And then we repeat the process if the still operation is not over. So every time we will take a byte from this location and we will add it. The result will be there in R2. Again, we take the next byte, again it will be added, again we take the next byte, again it will be added. Like this, we can add the element of array with help of this. So it is a very simple program for that purpose. Sometimes in examination also, such type of programs are being asked, that you add the elements of array which is stored at some memory locations, and the memory locations are given in the statement, and then you have to load the memory pointer with that memory location, and then get the data from memory location, and then add it and store it in some destination register. So that's all for assembly language instruction set and few programs. From the next lecture onwards, we will start the C programming for the ARM processor. Okay. If you have any questions, any doubt, you can ask. So by this, your topic number 2 is over. Any questions, any doubt?
No, sir, no doubt.